All right, guys. So here in Unit 4, we're going to continue making inferences. It's actually, all of Unit 4 is just more confidence intervals and hypothesis testing. But this time we're going to be looking at proportions rather than means, meaning the confidence intervals and the hypothesis tests we're going to be performing, we're going to be using to make conclusions about population proportions rather than population means. So starting off here, first of all, 4.1, this section is split up into two parts. So you can see here, this is 4.1.1, and I'll post a separate video for 4.1.6. So let's see. So starting with confidence intervals for a single proportion. So as we know, with all confidence intervals always equal an estimate plus or minus some margin of error. And with our margin of error, we've been using either Z star or T star as our critical value times the standard error or standard deviation of the population. Okay, so for proportions, what the actual equation ends up looking like is this. Our estimate for the population proportion is a proportion of our sample, which we denote with p hat. So again, p hat is a proportion from a random sample, which we are using to estimate p, the proportion of the population. In fact, I might even make a note here. P equals the proportion in the population, the full population. And that's what we're trying to make an inference about here. P hat is the proportion of our sample, and we can find the proportion of our sample by taking x, the number of successes within the sample, divided by n, the size of our sample. We're going to see that a lot. So that's our estimate. And then, of course, we do plus or minus our margin of error. And for proportions, we are going to use a normal distribution to do this. So we use a Z star as our critical value, which means for a 95% confidence interval, Z star would be 1.96. And for a 99% confidence interval, our Z star would be 2.576, just like before, no difference. Okay, and then we have the standard error. And the standard error, as we know from before, is the standard deviation of our sample. And we've seen this formula, this part of the formula before. We've taken the standard deviation for a sampling distribution of proportions in a previous unit. So this should look very familiar. It is the square root of p hat, our proportion from our sample, times 1 minus p hat, the complement of the proportion from our sample, all over n, our sample size. So altogether, this is the formula that will give us the confidence interval for a single proportion. Okay, so just like in the last unit, we will eventually talk about when we have two samples or two proportions and how we can do the same thing there. But of course, we're starting with the basics. All right, so p hat actually has a sort of binomial distribution. Binomial distribution. Remember, in a binomial distribution, we take a sample of a certain size and then we count how many successes we have. So when we're looking at a proportion in a sample, we are actually looking at a binomial type setting. The only thing though with a binomial setting is that when we're taking a sample, each time that we take a item out of the population, we're going to change our population's proportion slightly. So we do have the rule that our population needs to be fairly large compared to our sample in order for it to remain independent. Okay, but moving on. With binomial distributions, we know we like to approximate the probabilities of binomial events by using a normal distribution. Okay, and the conditions for using normal approximation in a binomial distribution are the exact same as they were in a previous unit. NP has to be greater than or equal to 10, and n times 1 minus p has to be greater than or equal to 10 in order to use normal approximation. Of course, in this scenario, we're not looking at a population proportion, we're looking at a sample proportion. So these p's are actually going to be p hats. So p hat has the approximately the normal has a approximately normal distribution. And as we know, we need to know our standard deviation and our mean of our sampling distribution for proportions. So here they are. If we are using a normal distribution, the mean of that normal distribution will be just p, the population proportion, which we're going to estimate with p hat. And sigma, our standard deviation of our sampling distribution for proportions, when we're using normal approximation, will be this, exactly what I said above when we were writing our standard error, p times 1 minus p over n. Okay, and then here on the side, we have just a reminder of our common critical z-stars that we use when conducting a confidence interval. We use this one, 1.96, most of the time, and then the rest of the time we're usually using 2.576, which your book usually rounds to 2.58 as well. Either way is fine. All right, so we have an example here that was done in the Apex video. I'm going to go through it a little bit more in case any of it did not make sense. So we have an example here. It says, in May 1998, a national poll of 1,007 adults found that 443 of those polled planned to watch the final season of Seinfeld. Construct a 95% confidence interval for the proportion of adults who plan to watch the show. All right, so in order to do a 95% confidence interval, I'm going to first go ahead and write down the formula that we used for confidence intervals above that I highlighted. P hat plus or minus z star times the standard error, which is p hat times 1 minus p hat, all over n square rooted. So you can see we have some things that we need to find before I can just plug things in and solve. So the first one is p hat. So p hat, as I said above, is x over n, where x is the number of successes and n is our sample size. In this case, we have 443 successes out of 107 adults that were polled. Which gives us a p hat of, using my calculator, 0.4399. Okay. Next thing I need my z star. We are doing a 95% confidence interval here. So from my table, I can see that I am going to use the z star 1.96. And then lastly, I need n, which I've already actually identified. I said up here, n, the number of people in my sample is 1,007. So there we go, that's all I need. So I can go ahead and plug it in and solve. P 0.4399. I'll go ahead and round to 0.44 plus or minus z star 1.96 times the square root of p 0.44 times 1 minus p, which would be 0.56, right? 1 minus 0.4 is 0.56, and n is 1,007. And then we go ahead and grab our calculator and start punching in numbers, starting with the numerator underneath of our radical, 0.44 times 0.56, and then dividing by 1,007, and then square rooting. Make sure you follow your order of operations. So that gives me my standard error. Here is 0.0156. So I multiply that by my 1.96 to get my margin of error, which is 0.0307. And then I'll add and subtract that from 0.44 to get the bounds of my confidence interval. When I subtract, I get 0.409. And when I add, I get 0.4707. So there we go. There's my 95% confidence interval for the proportion of adult Americans who plan to watch Seinfeld in May 1998. So again, with confidence intervals, that means that we are 95% confident here that the two population proportion for adult Americans who are going to watch the final episode of Seinfeld is within this interval. That's what we are saying here. All right, the next thing they talk about in APEX is finding the sample size when we're given a margin of error. So the margin of error from the equation for our confidence interval above, we said is Z star times the standard error, which is P hat times 1 minus P hat all over N and then square rooted. Okay, now of course I could plug in the given margin of error here, my Z star and my P hat, and then use that equation to solve for N within this format. In the APEX video though, they do go ahead and create the inverse or construct the inverse of this equation so that we can solve for N more directly. Now the thing with this N formula here, which I'll write down, is that if you don't remember this N formula, it still is okay because we can use this format, the formula for M, to find N as well. Okay, so notice when I wrote this down, instead of doing P hats, I wrote P stars. And that is because when we are looking for the sample size, we don't yet have a sample to take a proportion of, and so we can't have a sample proportion. So rather than having a sample proportion, we're going to have a guess at a proportion, or like a hypothesis for our proportion. So P star is our guess for the population proportion. Okay, again, we have this P star in this case because when we are looking for a sample size to take, that means we haven't taken a sample yet, which means we can't find the proportion of that sample, so we don't have a P hat. So the next question is, well, what if I can't guess P star? What if I have no clue what it is? Well, we're talking about success versus failure here. So if you have no idea what P star is, we can go with our most conservative guess, and that would be that we would have a success exactly half the time. So our P star would be 0.5. 1 second. Doop. Which means half of our outcomes would be successes and the other half would be failures. This is, again, our most conservative approach. It is going to give us the widest confidence interval for proportions here as well. When I put in 0.5 here and here, our formula for N ends up being a little simpler. No, 0.5 times 1 minus 0.5 is going to be 0.25. So when I multiply that by this Z star over M squared, it ends up looking like this instead. Okay, but again, I don't necessarily need that truncated formula there. I can still use this formula for N, plug in 0.5 here and here, and eventually it's going to simplify to this anyways. Okay, just knowing or recognizing this simplified version of the formula when you're using 0.5 as your P star is simply going to save you some time. But again, it's not one of those mandatory things to memorize. So let's go ahead and do another example. Here is a national poll conducted some months ago. From the 59% of those polled thought the U.S. Senate should ratify the Comprehensive Test Ban Treaty, the treaty that bans testing of nuclear devices by all countries. The polling company must do another pull if they want to have a margin of error of at most 4% for a 95% confidence interval. Find the necessary sample size. Okay, we're looking for sample size, so I'm going to go ahead and use my green formula up here. N equals Z star over M, all squared, times P star times 1 minus P star. Okay, so let's go ahead and find the numbers that we need to plug in here to solve for N. So let's see, to start, I have a Z star here. We're doing a 95% confidence interval, so that means our Z star is going to be 1.96. Then we have M. M is our margin of error. It says here that the polling company must do another poll, and if they want to have a margin of error of at most 4%. So our margin of error is at most 4%. So M is 0.04, 4%. And then we have our P star, our guess at our proportion. Well, based on a previous poll, the proportion was 59%. So a good guess here would be to guess the proportion is unchanged and therefore it is still 59% or 0.59. So let's plug all that in and see what we get for N, our sample size. All right, so I'll start with my parentheses, 1.96 over 0.04 is 49 exactly. And here, 1 minus 0.59 is 0.41, which I can then multiply by 0.59 to get 0.2419. Then I'll need to square root my 49, or not square root, square my 49, and then multiply it by 0.2419. So I get a final answer of 580.8019 on my calculator. So remember here, N represents the minimum sample size that we need to make this happen. That means any sample size less than this number is not going to be big enough. So even if the number after my decimal is less than 5, we're always going to round this up. So my N, the minimum sample size I need, is 581. We cannot take a partial sample. We cannot sample half a person. So it has to be a whole number. All right. Next thing here is calculating a confidence interval for a proportion with a graphing calculator. So let me get my graphing calculator out, and the instructions for this, of course, are on the next page of your study guide. So we have here the exact same, oh no, it's not the exact same, I think another one. I don't know if my calculator is going to open. 1 second. There it goes. Oops, now I got too many. Okay, so it says we have a recent poll of 1,031 frequent flyers, people who travel by air at least 5 times in 1 year. And it showed that 464 of the people polled were satisfied with the width of their seats in their airplanes. Follow the instructions in your study guide right here and use the one prop z-int feature of your calculator to find the 95% confidence interval. So this is the function in our calculator we're going to use. So to kind of decipher this, this means that we have one sample here. We're trying to estimate the population proportion. Z means we're using a Z star or a normal approximation. And INT means we're looking for a confidence interval. So to get to that function in our calculator, the instructions are right here. We're going to click the stat button, and then we're going to move over to tests, and then scroll down to one prop z-int and hit enter. So let's do that. Clear that out. Oops. So I go turn it on there. Ooh, okay. So I click the stat button, here, move over to tests. And I'm going to look for 1 prop z interval. So I see 1 prop z test. We're not doing a hypothesis test though, we're doing an interval. So 1, 2, 1 prop z interval right here. It's my option A. Again, depending on your calculator, it may not be A though, so make sure you double check and scroll down. So I'll click enter there, and it asks me for some information. X, of course, is the number of successes. How many successes did we have in this survey? 464. N, what's the sample size? 1,031. And lastly, C level, what's a confidence level we want to calculate? They say here 95% confidence interval, so I'll leave it as 0.95. Calculate, and I get my answer, along with my p-hat. So my answer is from 0.41968 to 0.48042, which they also have down here as their answer. Okay, so that is it for this video.